Greetings, let's look at this proof of G is a tree if and only if it's connected and the number of edges is number of vertices minus 1. And we already have a layout prepared here. We'll do implication from left to right and from right to left. So to first do the implication that if it's a tree that has this number of vertices based on edges, so edges equals vertices minus 1. Let's do it by induction. So what we can do is we can say that for the case that if this is 1, then that's the case of 1, then obviously it works out. Edges should be 1 minus 1 is 0, because if we have one vertex, there's no edges around it if it's a tree and connected. So that's right. And let's suppose this is k plus 1, so k plus 1 vertices. Then what we have is the number of edges under that circumstance would be k. And now let's remove from this hypothetical next case, k plus 1, not just k but k plus 1, let's remove from it a leaf. So minus a leaf. Well, if we remove a leaf is that vertex that's connected to that edge that connects it to the rest of the graph, but it's just one edge connecting this one vertex, and if this edge is cut off, then the vertex is also lost, this leaf vertex. So if we remove that leaf, the edge that connects it to the rest of the graph is lost as well. So if we remove a leaf, we get from k plus 1, we remove a vertex, so we get back to k, and then the edge set will reduce by just as much, exactly by 1 also. So we have k, and this will be back to k minus 1. So we sort of got into the situation that we got k plus 1, but if we remove it, we went back to 1. So we suppose that it works for k, and then we looked at k plus 1 scenario. We see it works just the same way. K plus 1, the next case, but again, the relationship between the number, now if the vertices is k plus 1, again we see we remove 1, we get the number of edges. And another way to talk about is we basically got into the situation that we get k plus 1, k minus 1 plus 1 here, which would together be k, because k minus 1 plus 1 on the outside, well, not this in the parentheses, so it doesn't look like multiplication, but k minus 1 plus 1 is the same like k plus 1 minus 1. So that was induction layout, sort of. For the other side, so if this is the case, then and it's connected, plus connected, that implies G is a tree. Well, let's look at this proof. Well, let's suppose the contrary to this, to get a contradiction and contradict that. So let's suppose G is not tree. In that case, what we can do is we can remove some edge on then actually if it's not tree, if I suppose that it has a cycle inside itself, all right? So this graph has a cycle. So remove some edge from a cycle, because it must have a cycle, not tree, and connected, so it has cycle. So remove some edge from that cycle that's there, whatever cycle there. But if you remove an edge from a cycle, think about it twice, it will make sense. If you remove an edge from a cycle, the graph's still connected, no vertices lost. So where we get is basically, we would have, if this was the assumption in this implication direction, we would now we would now have that the number of vertices is like this. But unfortunately, this doesn't work out, because the minimal amount of vertices you have in relationship to edges is minus 1. Think about it. If you have a connected graph, and I mean the simplest one you can think of is, for example, this. You have 2 vertices, but you must have, for it to be connected, at least one edge. So the difference can be at most 1, but here it would be 2. That's too little. Imagine 2 vertices, and if it was supposed to be amount of elements in V minus 2, then it will be 0 by the logic of, for example, this example. It will mean there will be no edge allowed here. That's a contradiction. It must be connected. So that's a contradiction. That leads to a contradiction. So we contradicted the claim that G is not a tree, so therefore it is a tree. So we also imply that if this holds, then this holds. The first part said that if this holds, then this holds.